Hello everyone, welcome to the module 2 of the climate guide by Climesumer. In this module, you will learn what climate change is and why it is important to act now. It is going to be quite a long video, about an hour, but it will be worth it, I promise, because I will explain everything in depth from start to finish. I hope that you will walk away empowered and ready for more. There are timestamps in the video if you want to jump to specific sections. And without further ado, let's dive right in. 2023 has been the hottest year on record. We had an average temperature of almost 1.2 degrees. 1.5 degrees is the limit that has been set by the Paris Agreement to avoid the worst effects of climate change. I hate to break it to you, this year, 2024, already has been off to a hot start. We can see that March has been the hottest month on record already. So it's very likely that this year will be either the hottest year again or the second hottest year coming after 2023. And we've seen some crazy weather extremes in the last months, in the last year. We've seen heavy rainfall events, glaciers melt, sea level rises, more intense tropical cyclones, and substantial damage to ecosystems. Now, here are just a few examples of the weather extremes that we've seen in 2023. This was the largest wildfire in Canada, and it was 2 times more likely due to climate change that it happened. On average, wildfires burn about 2.5 million hectares in Canada each year, and in 2023, wildfires have already burned 14 million hectares. You might remember this picture here from New York, where the wildfires created smoke and had for a short time the worst air quality in the world. We've seen extreme drought where China had another temperature record of 52 degrees, and we've seen other temperature records in Catalonia, for example, with 45 degrees, and we've seen other examples in the US, parts of Nevada, Colorado. We've also seen extreme flood events in September 2023 in Spain, for example, in Greece, in Bulgaria, and Libya. These floods have been made 10 times more likely and up to 40 times more intense with climate change as the cause compared to a scenario where climate change would not exist. And we'll get to how these things have been calculated going forward in the video. Globally, the temperature gets hotter, but how it affects us in everyday life can be through extreme flooding, through extreme heat, extreme drought, fire. So we get weather extremes, right? And these are just some of the climate change indicators that let us know that climate change is happening. And before we dive really in, I just want to get one thing off the ground. Climate change is real. Climate change is caused by us. It's pretty bad at the moment. Scientists agree. And there's hope. These things should be the baseline for us to discuss everything that I will say in this module and in the coming modules. And in this module, you will learn why all of these things are true, essentially. Now, let's start with the basics. A lot of people confuse the concept of climate versus weather. When you look outside of your window, you can see the weather. Is it sunny? Is it hot? Is it cloudy? Is it rainy? Is there snow on the ground? The weather refers to an atmospheric condition that occurs locally over a short period of time, that can be minutes, hours, or days. The climate is a typical weather condition over a long period, let's say around 30 years or more, and it describes the average weather over a specific time in a place, in a region. We have different climates across the world, just naturally. There are tropical climates that you see here in red. We have triclimates. We have, continental climates and really cold climates like in the Antarctic. And those are totally normal weather conditions for these times of the year in these places around the world. In short, we could say that the weather is what you get when you look out the window, and the climate is what you expect. When your grandparents tell you, when I was young, weather in the summer used to be like this and that, that is from years of experience, how they experience a typical summer in their region where they live. And that is the climate, because they have data points collected from their own behavior over, many, many years. So this is the difference between weather and climate. And what we see is that the climate worldwide is changing. And we can see that it's dramatically changing by just looking at the weather extremes. So we expect a certain climate, but what we actually get are weather extremes. And that is called climate change. So why does the climate change? It's a valid question to ask. We know that the global average temperature is rising, and that causes many of the weather extremes that we've seen already. Now, the global average temperature is rising because of the greenhouse gas concentration. So we are getting more and more greenhouse gases in our atmosphere, which heats up our planet. And I'll get to the greenhouse gas effect in a second. And we are adding more greenhouse gases because of human activity. Now let's break this down into the different steps and look into them. The first one, the temperature is rising, right? If we just look at the data that we can collect with sensors and measuring devices, we see that the temperature is constantly rising year by year. There are a few exceptions where it breaks out and then goes back again. That is somewhat to be expected, that the weather is not always constant. But we see that the global average temperature, and that is what everyone talks about with the Climate Paris Agreement of 1.5 degrees, is rising. And we see that compared to the 1800s, that's where the sort of the baseline before the Industrial Revolution, we are already approaching over 1 degree, right, with 2020, 23, 2022. And 2023 was almost 1.2 degrees of warming, right? And we can see that here already breaking out slightly. So that is one graph or one visualization that shows us how temperature is rising over the last years. When we look at the greenhouse gases, or in this case, the CO2 emissions, we can see that CO2 has been rising since the Industrial Revolution. If we look at this graph, we see the carbon dioxide over 800,000 years. And how we get to this data, we will also see in this module. But for now, what is important is that we see that the CO2, the carbon dioxide, actually crazily increased since the Industrial Revolution, you could say, since 1900 something, right? And you see the atmosphere has been changing constantly. And we've been through different warming and cooling periods of the planet. That is totally true. But we are seeing here a never before measurable increase in CO2 emission and also increase in temperatures. This current warming that we're experiencing is roughly 10 times faster than the average rate of warming after an ice age. And the carbon dioxide from human activities is increasing about 250 times faster than it did from a natural source after the last ice age. So yes, climate has been changing through 800,000 years, of course, but it has never been changing that fast on this planet. And that is concerning. Now, let's look at this greenhouse gas effect, because the greenhouse gas effect is really what creates that correlation, that connection between the global average temperature and the CO2 emission or the greenhouse gas emissions. The sun reaches the earth, and some of that energy, some of that sun is being radiated back into space. Almost like a mirror. If you hold a mirror into the sun, some of that sun of the mirror is being radiated somewhere else, right? And some of that heat or some of that sun is absorbed by the planet. For example, if you have a black sheet of paper, less sun is being radiated back into the room versus if you would use a mirror where basically all of the sun would be radiated back into the room. And that is sort of what the atmosphere is doing. The atmosphere is trapping some of that heat that is being radiated back into the atmosphere. And that's why it's also called the greenhouse gas effect, because in a greenhouse the same thing happens. The sun goes into the greenhouse, some of the sun is being radiated back, but because there's a glass ceiling, the heat that is trapped in the atmosphere in the greenhouse can't escape. You can't open the window. It's like opening the window of the greenhouse, but we can't open the window because we have this atmosphere that we can't really change. So that is why the more greenhouse gases are in the atmosphere, the more heat is trapped. And that's why the planet is warming, the more greenhouse gases we emit into the atmosphere. Now, what are greenhouse gases? Greenhouse gases are a number of different gases, and the most common one that we hear and talk about a lot is carbon dioxide. Carbon dioxide is a vital component of the atmosphere, is released through the natural process like volcanic eruptions and through human activity such as burning fossil fuels or cutting down trees, for example. But also carbon is stored in plants. They take out the carbon dioxide from the earth and together with the sun, they use it to create plant matter, to create the thing that we see as a tree or as a green leaf, for example. So that is carbon dioxide. And then there's different other gases. I'm missing an E here, but I'm not going to change it now. There are other gases that have the same greenhouse effect, so that also warm the atmosphere besides carbon dioxide. And the crazy thing is that they're more potent, they're more crazy than carbon dioxide. So 87 pieces of carbon dioxide is 1 piece of methane. That is what I mean here with potency. Over a 20-year time frame, this is the potency of methane, and over a 100-year time frame, the potency decreases to 20 times of that of carbon dioxide. So actually, when we add new methane to the atmosphere, it is even more harmful in like the next 20 years than it is harmful in the next 100 years. Where does methane come from? Methane comes from plant matter that breaks down. For example, it is released in wetlands, it is released in landfills, it also is released in rice farming. But most importantly, it actually comes from animal farming, where methane is being emitted by the digestive system of cows, for example. So when cows poop, their body releases methane, right? There's other sources where methane is released, and that is from leaks of fossil fuel production, used to heat your home, for example, or that you might use in your stove. That is called natural gas, is literally the same, it's methane. The gas that we use in the house is methane. And that methane can leak in the production, in the transportation of the gas, in pipelines, and it is very, very dangerous. And these leaks haven't been really identified or probably not really reported enough. There's also a video link in the description where you can learn more about methane leaks. And then we have a nitrous oxide, which is 265 times more potent than CO2. It is also produced by some farming practices. For example, when there's organic fertilizer produced and used. It is also emitted by burning fossil fuels and burning vegetation. And it has increased by 18% in the last 100 years. 1 stone of nitrous oxide is 265 stones of carbon dioxide. So if we would want to reduce carbon dioxide, we want to be like super effective, we would just need to find 1 nitrous oxide stone and would save a lot of work because we wouldn't need to find 265 stones of carbon dioxide. Of course, these are not stones, these are particles, right? But that's sort of like a way to think about it. And then we have chlorofluorocarbons, CFCs, and these are 10,000 times more potent than CO2. These are chemical compounds that don't exist in nature. They are totally produced and introduced by industrial processes. And for example, they have been used in refrigerants. There has been methods where refrigerant has been collected again to keep it from releasing to the atmosphere, because obviously that is a super effective way to hinder greenhouse gases from rising, because it's 10,000 times more likely. And there is, of course, a scientific method to express all of that, and that is called CO2 equivalence. So equivalence simply just means that we express everything, every greenhouse gas unit, in carbon dioxide equivalents. So that means if I want to refer to 1 stone of nitrous oxide, I would say 265 carbon dioxide equivalents. That would be the same as saying 1 nitrous oxide. We use carbon dioxide as the base and measure everything else against that base. And if we look at how these different gases are in the atmosphere, we see that carbon dioxide is by far the biggest, right? That's also what, of course, most plants need, so it makes sense that this gas is mostly in the atmosphere. Then we have some methane, 70%, nitrous oxide, tiny bit, and then these crazy industrial gases, just very few, which is good because of the potency. Let's look at the carbon cycle. That sort of explains in a nice visual picture how carbon is created and used. We have the sun, we have some plants, we have fossil fuels. There's carbon dioxide in the atmosphere. And when the sun is shining and plants grow, this carbon dioxide is taken up, so like used, eaten by the plants. And then these plants create plant matter, leaves, trees, wood, these kind of things. And at some point the plant will die. And if we don't use it, really, like if we don't cut the tree and make a table out of that wood, this wood will decompose. And over very long, many thousands of years, it will be buried in the ground with a lot of pressure and decompose and sit there until we dig it out. And essentially, all of that energy from the sun is more or less stored in that black stuff that is in the ground. And we can dig that out. That is the oil, for example, that we find, and refine that, the gas, the oil, and we can make fuel or energy out of it, right? Mostly fuel to use or to run engines. And when you think about it, the sun has energy. When you go out, you feel the heat, right? And all of that energy is really stored in this plant matter in the ground. And also that's why fossil fuels are so powerful. Yeah, and we also see that the animals, the cows, they poop methane as well. And plants also release some of the CO2 back to the atmosphere as well. All of that stuff we're digging out of the ground in a very, very short time frame, basically since the Industrial Revolution, since the last 100, 200 years. We're digging it out and burning it very, very fast. So that means we're taking all of the carbon that was stored in the plants and releasing it back into the atmosphere faster than the natural cycle would usually do it. And that is causing the problem. Now, what are the drivers of climate change? I already touched on this a bit, but let's look deeper into it. We already understood this connection between the temperature rise and the greenhouse gas effect, and that is connected to human activity. And when we look deeper into the human activity, we see that the problem of us putting more greenhouse gases in the ground comes from burning fossil fuels, from taking the stuff out of the ground and burning it fast. That is coal, that is oil, and that is gas. The second big thing that humans do is the clearing of land, also known as deforestation. That has a lot to do with the agriculture and meat consumption. Here's a cool graph from 2020. And what we see here is that essentially most of what we do needs energy, and in the past, most of what we've done where energy was used, we used fossil fuels to power it. And then we have the second most biggest thing that we need to do to survive is have food. Yeah, we need to eat. And that's the rest of these greenhouse gases that we emit. So those are the global greenhouse gas emissions by sector. And when we look closer into it, we can see that from the energy that we use, energy use in industry, so that is used to produce things that we buy, and you see that iron and steel has a huge chunk of it. The second big thing is transport. That is from road transport like trucks and cars, aviation. So just actually a tiny bit from the global greenhouse gases is actually from flying. And then some of it is from shipping. And we'll get into these different sectors later in all of the modules that are still yet to come. But this is just a high-level overview. And this is, we have some from residential buildings and commercial. So energy use in buildings that is used to mostly heat our homes. For example, my parents still have a fossil fuel, a oil heater. We literally have a oil truck coming to us every year, every second year, and we have tanks of oil in our cellar and a machine that literally burns that fuel to essentially to heat up our water and to heat up our home, right? Like we heat the water and then the water is being pumped everywhere, and that's how we heat the home. Not just we, how most people around the world, at least in industrialized countries, heat the home. So that is how energy or fossil fuels are used in the home. And then we have some other emissions that are not relevant for now. So we see the biggest thing is from producing things, making things, from getting things from A to B, transport, and from living in our home, heating. And then the biggest other sector is agriculture, forestry, and land use. And you already see what's crazy, that from that agriculture, most of the things, or like 5.8, like almost a quarter, is from livestock and manure. That is animal farming, meat consumption. And then we have deforestation. And later in the module about food, we will see that deforestation, the biggest driver for deforestation are animals. So that is essentially, we can add that together. And then we have some bits left for agricultural soil and rice cultivation and crop burning. So that is one way to look at it. So now we know that most of the stuff that we do needs energy and we need food, right? And let's look at how the energy is split, how the energy sources are split. When we look at this graph here, we see that most of the energy that we are using by 2020 is fossil energy. It is coal, oil, and natural gas. We have some solar, which is increasing rapidly. We have some wind, biofuels, other renewables like hydro, and biomass, which is just burning stuff, like burning wood, for example. And this is another graph that just shows us the global greenhouse gas emissions by source. So we see here that by 2020, around our time now, we are emitting around 51 billion tons of CO2 equivalents every year. So what do we see? We have land use change, that is from deforestation, for example. And then we have fossil fuels. This is this blue line. And then we have this green line, which is land use and fossil fuels together. So this is CO2 emissions. And then we have greenhouse gases, which includes the other things like methane and the other greenhouse gases that I mentioned before. And that's how we end up at around 51 billion tons of CO2 equivalents every year. And that is a problem. We'll get to that later in this video. And the goal is, of course, to reduce that to zero. This is yet another graph to show us how it's distributed. So we see that 84% of global energy comes from fossil fuels, and just 10%, 11 comes from renewables, and that is nuclear, which is low carbon but not necessarily sustainable. So today it means that when we use energy, we unfortunately still use a lot of fossil fuels, which increase greenhouse gases, which increase the greenhouse gas effect. So that means that traps the heat in our atmosphere, which increases our global temperature. That is how these things connect. Now, one big question that is quite critical to answer is whether climate change is caused by humans. And because we can look at all of these graphs and see that CO2 goes up or greenhouse gas emissions go up, but the question really is, do these greenhouse gas emissions actually come from us? How do we know that this is our fault? Other factors that could influence climate would be the sun radiation, for example, or volcanoes that erupt, cosmic radiation, the number of animals on Earth, cows mostly. But scientists know that none of these can explain the dramatic increase in global temperature. In effect, natural effects would have slightly cooled the Earth's climate. So if we only take the natural elements, we would actually see a cooler climate today. So only the rise in greenhouse gas emissions can really explain that we have climate change. But the question is, how can we prove that these greenhouse gas emissions that are added to the atmosphere are actually coming from us? Or actually come from burning fossil fuels? I mean, if you ask scientists, they think it's a stupid question, but let's just look at this from the data point of view. The answer is by the different flavors of carbon. There's carbon-12, carbon-13, and carbon-14. And essentially what we'll understand is that the ratio of these is changing, and that's how we can explain that it's from humans. Let's look at carbon-12. Carbon-12 is mostly what is found in plants. So when plants take carbon dioxide, they mainly take the carbon-12 type of carbon. Carbon-13 is usually found in volcano or volcanic activity. And carbon-14 is a radioactive kind of carbon, and it breaks down over time. That is used for the so-called carbon dating. So if we find very old fossil bones from animals, for example, we can understand how old this is because of that breakdown of carbon-14. Very interesting side fact here. Those are the different carbons that we have. And there's this interesting weird graph. And it shows us the ratio of total carbon, that is this black line here, and carbon-13, that is this gold line here. And we see that this is 1800 and this is 2000. That we see since the Industrial Revolution, there's like point in time where humans have started to burn fossil fuels, burn coal, burn oil, burn gas, that this ratio of total carbon and carbon-12 has crazily changed. And why is that? It is because we have been adding carbon-12 to the atmosphere, therefore increasing total carbon compared to carbon-13. And since fossil fuels are made from plants, and plants are mainly made from carbon-12, we can for sure say that the greenhouse gases that we add are caused from us burning fossil fuels and adding greenhouse gases to the atmosphere. That is sort of the most clear way to say that humans are responsible for climate change. How is climate change measured? how do we even know, besides looking at the climate and sort of feeling that there's more weather extremes, but how is it actually measured by scientists? There's two ways. There is one way of us measuring the changes that happen today with today's tech, or tech since like Industrial Revolution, more or less. And there's the methods of us looking into the past, like 800,000 years past, that crazy CO2 graph that I showed you in the very beginning. These data points are derived from various methods that we'll dive into now. For today's changes, we can look at the climate change indicators. And weather extremes are just one of the climate change indicators. Here's a big list of climate change indicators. There is the global temperature rise, extreme weather events, ocean heating up, ocean acidification, sea levels are rising, we can measure that. Ice sheets are shrinking, glaciers are retreating, they're getting less and less. Arctic sea levels are declining, snow cover is decreasing, and biodiversity is also decreasing. Let's look at the graphs for each. Here we can see the global average surface temperature. We've seen some of these graphs already. That spinning thing was the same data. And we see that this is here crazy increasing the more we go to 2020 to the current dates. And we're here reaching 1 degree of warming. And if we would add the ones for 2023 here, we would probably be here somewhere by 1.2 degrees already, which is dangerously close to 1.5 degrees that we want to try to stay under. This is the daily sea surface temperature, and we see that by August 23, where I looked up these graphs, that this has been quite high, higher than usual, and 2016 has been an outlier as well. We see the more we go into the past, the colder it is. Recent years, we see the higher it gets. This is another graph where we see the ocean heat, and it just goes up. This is oceanic pH, that is the acidification of the ocean, and we see that it drops. This is million years before present. Here we see a coral reef that died, and that will happen to most of the coral reefs that we know by 1.5 degree, and it's already happening here. We can see that. The ocean can trap huge amounts of heat. The ocean has absorbed 90% of the warming that occurred so far. The ocean can only absorb so much before things start changing. And the sea level rise is actually not because of extra water being added from the ice that is melting. It's actually because the ocean is heating up and warm things expand. And so the water is expanding, and that's why the ocean is rising, because the ocean gets hotter, not because we add more water. That is the main driver. And yes, these white things are dying corals that are turning white. This is a graph of sea level changes, and we see that this one here is actually satellite data, right? And then we had here global dam projects where they just measure tide gauge data. This is a video of ice in the Arctic. And here we see the graph, the time. So this is, now we're in the 1990s. And this white thing here is the ice that changes. And of course it keeps changing, it's dynamic, right? But we'll see the closer we come to the day, the less ice we'll have. All of that gets less and less. We're already 2015, 2020. Here are some pictures of glaciers that have been completely gone. 1909, 2004. You see that an entire glacier just vanished from the face of the earth. And of course, it looks nice, but there used to be a glacier. And there's this wonderful 2 websites that are also linked in the resources on Climesumer, and where you can see these different photos of before and after of sea level and ice sheets and glaciers. And this one here is the last chart of this section, where we look at the biodiversity. Essentially, they look at a number of different species. They count these species. The biodiversity over these many species and many, many populations has been decreasing by definitely over 50%. And that is crazy and very sad. Now, the second thing that we can look at is the historical data. So that is all of the data that we can't directly measure today with measuring devices that are like taking data points as we speak. And we have different tools to our disposal. We have ice core data, we have lake and ocean sediments, tree rings and glacier rocks, fossils, corals, and ship logs. And climate scientists, they call these Paleoclimate records. This is how this looks. It's so crazy. So they use machines like this, and they go to the Arctic where like a lot of untouched ice is, and they drill very, very deep into the ice. And because the snow is falling every year, and then ice is sort of like going down, it is a very good indicator of how climate and weather or the atmosphere used to be many, many thousand years ago. So we get these ice cores from the Arctic, for example, and then they're stored in these huge labs, or actually I think just a few labs around the world, and they're cooled down, and then these are analyzed and measurements are being made with them, and that's how we get these crazy 800,000 years carbon dioxide graphs, for example. Another way to do it is sediments from the ocean or lakes, and you see it's the same idea. You drill very deep down where not a lot of things happen over the many thousands of years, and you can analyze this and get data out of it. So with this, you can trace climate back 5 million years, which is insane. So these are sediment cores. And you see that it's not super accurate, but it's a huge time frame as well. And then for rather like a bit more recent climate, you can also use tree ring data. Trees can live for hundreds of years, sometimes even thousands of years. And over this time frame, a tree can experience a variety of environmental conditions: a wet year, a dry year, cold years, hot years, early frosts, forest fires, and all of that. Every ring is 1 year, right? If you count the rings, you understand how old that tree is. And they are sensitive to local climate conditions, such as rain and temperature and humidity and so on. And depending on the climate, these rings change. So the tree might grow more or less depending on the climate, and have a bigger or smaller ring, for example, depending on whether it was dry or wet in that year. And that's how we can understand more recent past climate. Here is this as a graph again. So a small ring might be a dry season, a bigger ring might be a rainy season. So this was looking at the past in 2 different methods. Now there's also a way to sort of predict the future of how climate will be That's how we know that we should start changing how we make things and how we live if we want to have any chance of a nice, livable planet. Sounds crazy, but that's why I'm making this course, to provide hope and help people actually get this full picture, because it took me way too long to actually research all of that and understand myself, and I want to save you some time. Now, we've seen how we can look into the past, but there's also a way how we can look into the future, or almost predict the future, and that is by using climate models. A climate model is a simulation of all the factors that can affect the Earth's climate. They can cover a particular region of the world, they can cover part of a climate system, for example, or they can also cover global simulations of the atmosphere, of the ocean, of land, or of ice. There have been different models over the years, and all of them helped to basically create a global scale coupled climate model. They are, of course, based on physical and chemical processes of the Earth systems that are essentially represented by mathematical equations. Each model works by dividing the atmosphere into a three-dimensional grid and calculating what goes on within each box of that grid. So a scientist, they could input data from observations of temperature and humidity and pressure, and then the model would use physics to compute how weather will develop within each box, sort of that red area here. And then you can predict what effects those developments in that box will have on neighboring boxes, sort of a box here, for example. Then what effects those neighboring boxes will have on their neighbors, this neighbor. And this way you can understand the different effects over a particular region or the entire globe. The verticality is sort of the atmosphere above the ground or even within the ground. The horizontal grid is really sort of the map when you look from the top. There's, as I said, many different models, right? And CMIP is a approach to making the different models that are available comparable to each other. And each 5 to 6 years, there's a new global comparison happening. Currently, we're at CMIP 6, and CMIP 7 is under development. And you see the different things that are being evaluated and the different models that are being compared to each other. Another important aspect of climate models is the resolution. The resolution can be a spatial resolution, the height or the width, and it can be a temporal resolution, the time steps it uses or can look into the future or look back into the past. And CMIP 6 has a resolution of 10 to 100 kilometers as a grid. And you see this here. In the 1990s, you had models that had a resolution of 500 kilometers, and then it keeps getting more detailed and detailed the more we go into the present. They are being computed in huge climate computers. One of the computers that did most of the work in the past is the Mistral, was inaugurated in 2015. That is the actual climate computer. It was hosted in Germany, and it was used for the CMIP 6 simulations in the 6th World Climate Status Report. There is a new climate computer in the making, or I think actually it's live now, that can run higher resolution models around 2.5 kilometers square instead of 80 kilometer. And it can also look more into the future, so it can calculate longer time frames. The resolution is higher in both time and space. Previously, it was just a few months that it could look into the future. Now it's even longer. So this, for example, can predict the movement and behavior of clouds on a small scale, the interaction between the atmosphere and ocean and other parts of the Earth. So it's a pretty powerful computer that can model the climate. And a study from 2020 found that actually the climate models or the forecasts of scientists in the past are pretty accurate to the actual development that we see. So the red line is the observation, the blue is the different predictions that have been made using climate models. And crazily enough, just by using the greenhouse gas effect, scientists in the 70s already predicted global warming happening very close to what we see today, just by using the greenhouse gas effect. So that shows us that this is the main way climate change is caused. What these climate models allow us to do is to do something called the attribution science. Attribution science tries to understand how much more likely extreme weather events or climate trends are due to climate change, are due to human activity. So in the beginning, I showed you these pictures, right, of fire, of drought, of floods. And the question is, would they have happened the same way if climate change wouldn't exist? Or how much different are they because we are burning fossil fuels and because we are adding greenhouse gases into the atmosphere? And attribution science is exactly that science that tries to answer that question. And they used climate models to run predictions for this specific region where, for example, an extreme weather event happened. And then they can sort of say this event is 10 times more likely and 2 times more severe without climate change. There are 2 cool websites that track these weather attribution studies. The first is the worldweatherattribution.org website, and the second one is one from Carbon Brief. And there I also found these specific examples. There was a flood in Libya, 2023, where it was a 1 in 600 year rainfall event. This event has become 50 times more likely and up to 50 times more intense compared to a 1.2 degree cooler climate. And as we saw in 2023, we already touched this 1.2 degree level. So that means it's just way more likely and more intense that this event, as it happened. This is another picture of Libya in 2023. And you see this destruction that it caused. This is the flood that happened in Greece and parts of Turkey and Bulgaria in 2023. And there also has been done some attribution studies. And they found that human-induced climate change made an event as extreme as this one up to 10 times more likely and up to 40 times more intense. And again, you see the destruction that it causes and the sheer extreme of a flood. Here's a summary. 10 times more likely and 40 times more intense. 50 times more likely and 50 times more intense. These are crazy numbers. Now, this is the last big part of this video for the module 2 of climate change. And I promise it will get better, it will get more fun, and it will get more hopeful. Why is it important to act now? We have this graph that we've used to sort of have this red thread for this video. And we understood that the global average temperature are rising because we're adding more greenhouse gases to the atmosphere by human activity, which is mainly the burning of fossil fuels. and deforestation and agriculture and animal farming. And we learned that with rising temperatures, climate change effects are getting worse, unfortunately. And we know that climate models can be used to understand how different weather extremes, how likely they would have been and how more extreme they have been due to climate change. And we can also use the climate models to look into the future. Now let's have a similar model to why we need to act now. This is the three elements that we used to understand what climate change is and how it behaves. And our climate models tell us that we have something called a carbon budget. And I'll get into the specifics step by step. This carbon budget tells us that if we are over that budget, so if we reach that limit, then we will most likely reach more extreme weather events and we'll reach tipping points. Tipping points are things that we cannot really reverse. And on the flip side, what we need to act upon, what we need to do, is we need to get to a state that is truly sustainable, and experts call this a net zero world, where we ideally don't emit any greenhouse gases. Where this 51 billion tons that I mentioned that just goes up, where we take that down and reduce the greenhouse gas emissions. Now, let's take a deeper look into carbon budget. A carbon budget refers to the allowable amount of carbon dioxide emissions that can be released into the atmosphere while still maintaining a specific global temperature threshold, such as 1.5 degree as set by the Paris Agreement. Quite a scientific description. You could think of a carbon budget like this, a bucket of water. The bucket is sort of the budget that we have. We have a bucket that we can fill with water, and the water that we are putting into this bucket is the amount of CO2 emissions, or the amount of CO2 equivalents, greenhouse gas emissions, that we emit annually. That is this 51 billion tons of emissions, this crazy graph. That is the water that we add into the bucket. And of course, at some point, this bucket will overflow. That is why it's called a budget, because this bucket only has a certain size. And once this size is full, once the bucket is full, it will overflow. And when things overflow, things will start going sideways, and that is not good. When this bucket overflows, we are reaching tipping points. Tipping points are also calculated using climate models. And in the context of climate change, they refer to a critical threshold at which a small change in the environmental conditions can lead to a drastic and often irreversible change in the ecosystem or climate system. So crossing a tipping point may result in profound changes such as a rapid melting of ice sheets, buyback of forests, the alteration of ocean circulation patterns. And these tipping points can have cascading effects, causing long-term impacts on global climate, on sea level, on biodiversity. The fear is that once we reach one or more of these tipping points, we cannot transition back, and the system, our world, reaches a new state that we've never known. A less scientific description of this is like this Jenga tower. We can take some pieces out and it's still stable. It might be a bit shaky, but the more we take out, the more shaky it gets, and at some point it will simply just fall. And what we try to do is to not let this tower fall. And there are these climate models, they tell us that when this bucket is full, or when it starts overflowing, the chances for us that this Jenga tower will fall are increasingly higher. Our goal is to, of course, reach net zero, reach that sustainability thing where we actually reduce the emissions. We have this nice little bucket where there is no water coming into the bucket, and we have a stable Jenga tower. I know what you're thinking. AI was used to make that. And of course, what we try to avoid is this crazy thing where like everything just blows and nothing is really stable. Okay, let's look at the carbon budget. The carbon budget is a prediction of likelihood of global temperature based on a given amount of carbon in the atmosphere. I know it sounds a bit complicated, but once we look at this table, I think we'll understand more. So what this table shows us is the carbon budget from a start date of 2020. What we see here is the different degrees of global warming that we want to try to stay below. So here we have 1.3, 1.4, 1.5 degree, that very special threshold that we want to try to stay below because of the tipping points that I'll touch in a second. So we want to stay below 1.5 degree, and we can stay below 1.5 degree with a 67% likelihood, and that gives us the budget if we only use up 400 gigatons. So we have 400 gigatons left with a 67% success rate to stay below 1.5 degrees. If we, let's say, try to stay below 1.6 degrees, we have even a 83% success rate with the same carbon budget. But we also have a slight chance to stay below 1.3 degrees with the same carbon budget. Actually, we have a 17% likelihood that we'll stay below 1.3 degrees with that same carbon budget. So this 400 gigatons is a good benchmark for us to try to stay below. And there was a new study that found in 2023 that we actually only have 150 gigatons left if we, for a 67% likelihood to stay below 1.5 degrees. Because here the base year was 2020, and here the base year is 2023. Here is the 400 gigatons. So we're depleting it faster than we think, and we actually have less than we think. This graph here is our global greenhouse gas emissions by source. We know this graph by now. And it shows us that the greenhouse gas emissions, all greenhouse gas emissions together, are at 51 billion tons of greenhouse gas emissions that we are adding each year to the atmosphere. 51 billion tons of CO2 equivalents. Now let's do some math. If we take that 400 billion carbon budget from the base year 2020, that gives us the 67% probability or likelihood to stay below 1.5 degrees. And we have, let's say, 50 billion tons of global emissions every year. Then we have still 8 years left from 2020 onwards before we reach that 1.5 degree carbon budget. Now, it's 2024, unfortunately already, and not much has changed. That leaves us with 350 billion, right? The year's not over, but 300 billion tons and 4 more years to go. Now, if we are using this 150 billion tons, we actually only have 3 more years to go with that carbon budget, with that probability, right? we still have lower chances to stay below 1.5 degrees, but with good chances, a bit more than 50% chance to stay below 1.5 degree, we only have 3 years left, which is, you can guess it already, quite unlikely that we'll actually stay below 1.5 degrees, unfortunately. And this is the climate change tracker that uses all of the data that I just showed, where you can choose the different carbon budgets and the different likelihoods, and it will show you when it is exhausted. So our budget of 150 gigatons is exhausted in 2026. And of course, we try with that budget to go to zero, from 50 billion tons to zero, that we have this nice, sustainable world that will live on forever. That is the goal. Now let's look at tipping points and climate change effects. Because the tipping points are essentially the reason why this 1.5 degree threshold is so important. A climate tipping point, as I said in the intro already, is a critical threshold at which a small change in temperature can lead to significant and often irreversible changes in the Earth climate system. Now, this is a nice graph that shows us the different tipping points at different degrees. What do we see here? We see that we have 2 degrees, 4 degrees, 6 degrees, 8, 10. I hope that we'll stay definitely below 2 degrees. We see at 1.5 degree, which is very likely that we'll reach it, unfortunately, means that Greenland will not have ice left. It means that the West Antarctic ice sheets collapse as well. It means that tropical coral reefs will be dead. So, for example, the Great Barrier Reef will be mostly 99%, 90% dead. There will be places where permafrost will warm. Mountain glaciers will go. And then there's even more things, right? There is Amazon rainforest dieback at 2.5, 3 degrees. And there's actually new forests creating itself at 4 degrees. There's another view that makes this more visible on a map. So low latitude coral reefs die off, that is below 2 degrees, all of the orange ones. Ice sheet collapse in this place. Greenland ice sheet will be gone. Permafrost will not always be there, which will, add lots of emissions every year when this happens. That's why this below 2 degree or 1.5 degree is so important. Some of these tipping points are already happening. Like we already see that, as I showed you with the climate change indicators, that these things are already happening. So we already lose ice, we already see coral reefs dying. So these things are real and they happen as we speak. Here is potential scenarios that we might reach, okay? This is from 2022, as you can see, our world in data. This is the 1.5 degrees pathway that we need to achieve. We are currently here, 2023, 4. We are here at our 50 gigatons of annual greenhouse gas emissions. And you see that we need to halve it by 2030, more or less half our emissions by 2030, and almost decrease it by 70% by 2050, to stay below 1.5 degrees in 2100. I know it's crazy time frames. This is what we should do. This is how the 2 degree pathway looks like. This is if all pledges and targets are met, what we will currently achieve, 2.1 degrees. This is what current policies are actually saying, alarming, 2.5, 3 degrees. And this is if we don't take action at all. And you see there's a pretty big stretch of what could happen, because climate models are not really powerful enough to predict all of the changes that will happen if we go 3+ degrees. This is another graph that shows the different pledges and the different scenarios. And we are trying to reach, to stay below this. And the most optimistic scenario is 1.8. Pledges and targets is in this range here, 1.6 to 2.5 degrees, 2 degrees. And pledges that have been done for 2030 get us to 2.5 degrees. And current policies and actions get us between 2.5 and 2.4 degrees. The next module of this climate guide will go into details of how every degree, 1.5, 2, 3, and 4, will actually change our life and what impact it will actually have. Definitely don't miss that, because this will hit even more. And I promise after that it will get better, because there are solutions. But as of now, you see the urgency. I want to show you one clip from one of my favorite movies that sort of illustrates this graph even better. That there is very good movements as well that create hope. But depending on where you look, you really feel like the following happens. That is from Back to the Future. They're running towards a cliff and go faster and faster. And that's sort of our current climate policies. They're not nearly enough. So this is the cliff. And we should be these people, right, that don't go to the cliff and make it work. And not be Marty McFly that goes down the cliff, or not be that train that goes down the cliff in a sec. See, Marty doesn't fall. But that train surely does. That is what happens if we don't act. This train right there. And I think it's not a overstatement. So what we just saw in the video is that this decade really is do or die, right? It also means that every single part of a degree that we stay lower saves millions of lives and matters. But it also means that if we just trust the politics and if we just trust the big oil companies, then surely we are running into 2, 3 or more degrees of a world with the potential of not even being able to reverse the changes and the damages that we have caused. Literally being that train that goes down the cliff, or being that world that goes down the fire. There is beautiful words from the Climate Tipping Point report. These tipping points pose threats of a magnitude never before faced by humanity. These threats could materialize in the coming decades and at lower levels of global warming than previously thought. They could be catastrophic, including global-scale loss of capacity to grow major staple crops. One Earth system tipping point could trigger another, causing a domino effect of accelerating and unmanageable damage. Tipping points show that the overall threat posed by the climate and ecological crisis is far more severe than is commonly understood. This will multiply crises in the same way that COVID-19 pandemic caused cascading stress to societies and economic systems globally, with unequal and unjust consequences. These impacts could escalate to threaten the breakdown of economic, social, and political systems, triggering destructive tipping points in societies experiencing stresses beyond their ability to cope. Stopping these threats is possible, but requires urgent global action. Even with urgent global action, some Earth system tipping points may be unavoidable. This is not my text. This is the Global Tipping Points report from climate scientists from 2023. And it couldn't be clearer that this picture is true, right? If we don't act today, then we might not have a chance to fix it. So climate action, to sum up this entire module, means that we are fighting for a livable future. We are not doing it for the planet, or we're not trying to be a bit more sustainable. By doing climate action, we are saving life as we know it. We are saving society, politics, and all of the things that we know are good. We are saving that from destruction. That's what's at stake. And in the process, we are saving ourselves. Now here, I want to say a huge thanks. If you actually stick to the very end, then congratulations to you. You are a really, truly curious person being, and you definitely care about climate change. I appreciate you a lot. If you want to learn even more, I have even more modules prepared. The following are the module 3, 4, and 5. Module 3, I mentioned already how 1.5, 2, or 3 degree world would feel like and how our everyday lives would change. Module 4 is sort of the promising overall positive module that tries to inspire you and show you one global way to think about climate solutions, sustainability on a high level framework, so that you can essentially go out and start doing the work where it matters without me or without anyone sort of having to tell you exactly what to do. You will be able to think for yourself and see what you can do. And module 5 will be the power of individual action and sort of who should fix climate change, because there's a lot of this claim that we as individuals can't fix it, or that the big corporates should fix it, or that governments should fix it. And the truth is that everything is interconnected. Companies are part of a political system. We are part of a political system. Individuals work at companies. That means also that everyone who is part of a system, that is literally everyone that lives on this planet, also has the power to change things. And I don't mean, putting the lid on your stove when you cook. I mean like actions that actually matter and that actually have an impact. And if you're impatient, you can go back to Climesumer.com and look for the climate actions directly. But if you're more interested in getting more input, then just continue watching the playlist or on Climesumer.com, the climate guide, and just watch the different modules. There's more input that you can watch and take what you've learned into your own hands and start doing. Thank you so much. Wish you a great day and don't lose hope.